give you everything else you need. So don't bring any extra paper. You'll be able to do your work directly on the midterm itself. And as I said, we'll be giving you all the equations and probably more than all the equations than you need. So you'll actually have to figure out which ones are relevant for which questions. And we'll give you all the constants, etc. So in principle, you shouldn't need to bring a cheat sheet. If you don't want to spend time on that, that's fine. But obviously, the way to study, as I've said, is look through your past problem sets, look through the notes very thoroughly that you've taken in class. And also, as of something like 15, 20 minutes ago, I posted the practice questions for this midterm on B-Space. And you should have already gotten an email about that. Don't check your email now. Yes?
Are there the same difficulties and questions that we'll actually have?
Yeah, largely. They're certainly covering a wide range of topics that we think are fair game for the midterm. But it's only 6 questions or something that we posted, so it's a little bit more than you would get on the midterm itself. But we're also sort of have a caveat at the top that this doesn't mean that these are the only things we'll be testing you on, right? So anything that really we've done in problem sets or in lecture are fair game, and for that matter, sections. Yes?
Will it include all material until the end of the day?
Yes. So if you ask me lots of questions, then I won't be able to get to all the material I want to, and then you'll have fewer things that you'll have to study for, so there's an incentive to be actively engaged. Not that there isn't already that incentive. Any other questions on?
Do you have a ritual that you should know about?
Do I have a ritual?
We have a ritual. 10 seconds before the midterm starts, you have to let us know so we can do a countdown and say blast off.
Are you serious? How did you collectively create this ritual? Is this cool with everyone that wasn't in 7A? Not cool? Okay, you can put in your plugs. And you didn't do it. Okay, that's fine. Yes. You have a problem with it? Yes. You'll start at 11:10, and you'll get notice of that 10 seconds before 11:10. Apparently, that's what we have to do. Okay. Yes. Holly.
Is there any chance you can post the equations that you're going to put on?
It's on. So they're on the practice already. We may add or subtract a few, but for the most part, if we make up the exam sort of with any amount of notice, we'll give you the exact final equations that we'll wind up giving you. But for the most part, they're already there. Okay, right. So sections as normal this week, that is, the sections will be referring back to the work we've been doing this week, starting tomorrow and then on Monday. And then on Monday night, as we've said, there's a review section run by your awesome GSIs from 6 to 8 p.m. And so, bring questions. Obviously, it will be good if you've already looked at the practice questions. And we will try to post, I think probably by Monday morning, maybe Sunday night, we'll post the answers to those practice questions. And so hopefully you've worked out some of these practice questions in advance of that, or you're really good at not looking at your email where you know where the answers reside. So we'll do that sort of in advance of the review section. But if you have questions, for instance, about those practice questions, bring those to the review section. But irrespective of what you all want to do, the GSIs are going to run through sort of an overview of what we've done already, just to give you sort of a big picture of how all the lectures tie together. The wiki has now been updated on B-Space with the current reading and all the reading that you're responsible for the exam. My office hours this upcoming week will be on Monday instead of Tuesday, and I'll just make that from 4 to 5. Are there any significant conflicts with that? Okay. So I'll leave it at that. And colloquium today should be fairly interesting. Doug Finkbinder, who's a professor at Harvard, is going to be talking about structures of the Milky Way. This is relevant for the stuff that we'll do after the midterm. In particular, talk about these new large plumes of gamma rays that are coming from the outskirts of the Milky Way, above and below the plane of the Milky Way, and also talk about how we make measurements of dust, which turns out to be quite important within the Milky Way. Any questions on overall logistics? Okay, so last time we talked about tides And in particular, we talked about extreme tides. And so this is when the differential force pulling two sides of something falling into something with mass something is larger than the force holding that something together. Right? In the context of people, we talked about the tensile strength of skin, and that might hold you together. You also have some amount of self-gravity, which is pretty negligible because you're standing on the Earth, and that's much stronger. But that's actually another calculation that I think you'll wind up doing in section. So that's obviously kind of just sort of interesting in and of itself. But we also saw the tides are at play, extreme tides are at play within the Milky Way, when we looked at comet Shoemaker-Levy and it getting ripped apart by Jupiter. What you'll see also in section is how these not extreme tides, but sort of normal tides are at play within the solar system. In particular, you relate this differential tidal force from the moon and the sun to what we experience on Earth, because these are the normal tides that you wind up experiencing. You'll see that in section. Black holes meets quantum mechanics. We talked about Hawking radiation. We talked about the singularity at the center of a black hole and how it may not actually be infinite density, but something like 10 to the 100 kilograms per meter cubed, which is something like the Planck density. We don't really know what's going on there, but it may be that there aren't actually infinities in the universe, that once you start crunching matter together in a small enough space, the graininess or the patchiness of space-time winds up sort of reigning supreme, and quantum mechanics becomes more important than GR on those very small scales and extreme mass densities. And then we started talking about black holes in nature. Were there any questions about what we talked about last time? Okay. So remember, we ended last class with a discussion of accretion onto a central body, and in particular, accretion around a black hole or a white dwarf or neutron star, a compact object. And we said that there's a certain amount of energy available if you take a parcel of mass at very large distance from this compact object, and you just move it down, its potential energy, in a totally Newtonian sense, no GR here anymore, can wind up getting converted into kinetic energy and slam into the surface of that star. Now, in the case of white dwarfs and neutron stars, there's a surface, indeed, and that mass can wind up either sort of liberating a lot of its energy as it winds up smacking into the surface of that star, or the mass can just sort of accumulate on the surface of that star. And over time, the mass of that compact object can start to grow. And if the mass winds up getting large enough, it turns out, and the densities are high enough on the outskirts of these compact objects, you can wind up essentially igniting some of that mass that you've added. So this is the origin of novae. This is the origin of X-ray bursts from neutron stars. Essentially what you do is you take the mass that's accumulated over a short period of time, you dump it onto the surface, there is some sort of thermonuclear runaway, and you very quickly liberate all the energy or the rest mass energy of what you accumulated. It's not all of it, though, right? There's some sort of efficiency for converting rest mass into pure energy. Remember, for fusion, that's something less than 1%. That's 0.007. We'll get back into efficiency in a little bit. Regardless of how we wind up taking this parcel of mass from large distance down to a very small distance, and how we take the kinetic or the potential energy and convert this into kinetic energy, we said that for any reasonable system where mass is being transferred, it makes sense that there's going to wind up being some angular momentum associated with this mass in falling. And this is how we wind up setting up accretion disks. So the general picture that you should have in mind when we talk about accretion disks is that we have what's called a secondary star, which itself can be quite large. Mass is transferred through a special point onto a disk. This is called the Lagrange point, or in this case L1. When the masses are the same, so the mass of this central body, this compact object, when that mass is the same as this mass right here, This is just the center of, it's basically L1 is just at a distance of A2, the semi-major axis, from each object. So we can actually work out some rough numbers that might be of interest here to figure out what kind of periods of these binaries we're thinking of. If we call this m star and it has an associated radius r star, a typical r star of a red giant, which is overflowing its Roche lobe through this L1, is something like 30 solar radii, which implies, based on what we just said here, that A is something like 60 solar radii, and that's of order 0.3 astronomical units. If, just for fun's sake, we say that m star plus m compact is of order 1 solar mass, it's actually a different kind of regime that we might be interested in the context of black holes, then using Kepler's law and the fact that p squared divided by a cubed is going to be a constant, since we're essentially positing that this system is overflowing its Roche lobe, we wind up having that the period is something like 0.2 times 1 year. Because we can basically use our own solar system because we posited we have the same mass. So this is of order something like 2 months. So for a generic system of mass, 1 solar mass, which has some mass transfer, onto this accretion disk, we're talking about periods of something like 2 months, which is pretty short. And in fact, the period ranges for binaries where you wind up getting a significant amount of overflow can be from hours to months. It depends, obviously, on the exact configuration of what the radius of the star is, the secondary, what the mass, total mass of the system is, etc. What's kind of neat is that we can obviously use Kepler's law, making observations of the Doppler shifts of individual lines within the spectrum of the secondary star as a function of time, and from that get a mass function, and then doing very careful modeling of the light curves, the luminosity light curves of the secondary. In these cases, all these things are secondaries, and all the compact objects plus their accretion disks are symbolized here. These are all two-scale depictions of real black hole binary systems in the galaxy. And you can see up there what that scale actually is. From the Sun to Mercury is an appreciable distance here. And some of the most famous black hole binaries are listed here. Sometimes the accretion disks are small. Sometimes the accretion disks are very large. But what's clear, if you've taken 7a and you remember how you wind up using Kepler's third law to get this thing called the mass function, is that you can then put limits, if you have models for what the masses of the secondary are, on what the masses of this unseen object is. And there's some recent work that's sort of summarizing all this. I'm not going to ask you to memorize any of these numbers or these overall size scales, etc. But I just wanted to give you sort of a flavor of current research on black hole binaries. This is a nice depiction of what's called the probability density of what the different masses are of the primary, of this compact unseen object, basically using the technique that I just described, measuring the Doppler shifts of the secondary and inferring the mass of the primary from that. And this is in units of solar masses. So 1 solar mass is down here. And remember, we said that the limit, or I don't know if I explicitly said this in class, but we think the upper limit for the total mass of a neutron star is somewhere in the neighborhood of 3 to 5 solar masses, right? So everything above 3 to 5 solar masses, where you're not actually getting any specific lines coming from that from that source. So it's not obviously a normal star. And in many of the cases, you can actually make the radius or infer that the radius is very, very small. Anything larger than 3 to 5 solar masses, if it's not a normal star, has to be a compact object. And if it can't be a neutron star and it can't be a white dwarf, really the only thing left, so this is sort of a process of elimination, is a black hole. And in some cases, the measurements of these masses are very, very good. The reason why these aren't measured perfectly in all cases is because there's uncertainties associated with each of these systems. There's an uncertainty in the inclination angle. These are things that you can maybe wind up inferring with very careful modeling. There's actually just uncertainties in the data, and all that stuff is thrown in and is manifest in a plot like this. So you can actually, I think, very quickly visualize that there are a large number of solar mass, or 10 solar mass typically, black holes in the galaxy. In addition, as I mentioned, there's some indications of very massive black holes. And in this case, a graduate student and another professor in the astronomy department here a few years back looked at an X-ray source, and we'll understand more fully in just a bit why this thing actually is an X-ray source. And this was actually in a nearby galaxy. It was a very bright source. They actually took spectra as a function of time. So here you have something up there, and you wind up seeing some characteristic line. I forget what this is. It's the helium-2 emission line. And you see they didn't plot this in units of wavelength. They plotted this in units of relative velocity. Why would they do that? Or how could they do that? Yeah, just Doppler shift, right? So they have a delta nu divided by nu rest, and that equals essentially v divided by c in the non-relativistic regime. It means that they can measure the location of where this line is as a function of time. It's wobbling back and forth. And from that, you can see the characteristic amount here, something like 1,000 kilometers a second, or maybe something like half that. Peak to peak, it is indeed about 1,000 kilometers a second. And this is changing over the course of just hours, right? Actually, sort of period of order 2 days. So from this, they get a mass function. And since the inclination isn't known, you wind up getting a lower limit. And that source in that nearby galaxy reveals that there is a black hole that has a mass something larger than 23 solar masses. So this is what's sometimes deemed an intermediate mass black hole. The origin of this is not really well understood. How you wind up getting sort of, say, a 25 solar mass black hole or even a 100 solar mass black hole is not really well understood from a evolutionary standpoint. Okay. So we also ended last time, I think last sentence of last time, is a statement that I made that the reason why this source of mass, which is plunging in, can actually make it all the way to the center very quickly is because there's some angular momentum associated with the system, right? So if you think about these two systems in orbit around each other and mass transferring, clearly there's some orbit of the parcel of mass which is getting transferred on, right? And so there is an angular momentum associated with that. Right. So the easiest thing to do is to say that there's a Keplerian orbit for the masses in the accretion disk. And these orbits will basically wind up decaying, right? So instead of just sort of being in a happy orbit at large radius from this central body, these masses are going to wind up feeling essentially this, this migration inward towards this compact object. And that happens through what are generally deemed viscous processes. And sort of a more general statement about viscous processes is that there's some sort of friction between these various parcels, right? So you have some mass which is falling along some Keplerian orbit in the accretion disk, and you have another mass at a slightly different radius increasing here, different little mass parcels of delta M. And these two little parcels are actually touching each other, right? And so if you have any heat associated with these parcels, think of these as just parcels of gas. then there's going to be some back and forth motion here in the radial direction. You wind up getting these parcels interacting. You wind up getting overall friction. And that friction serves to decay the orbits of both of those parcels. A specific source of that might be magnetic fields. And in particular, you can imagine if indeed this accretion disk is hot, that you would have some ions associated with it. This wouldn't just be a neutral accretion disk of neutral hydrogen flowing in, right? You actually have some ionized gas. Ionized gas, where you actually have free electrons around, are moving. What are you doing? You basically have magnetic fields, right? You create magnetic fields. Those magnetic fields can interact with the other charged particles around them, right? Also creating this sort of frictional drag on the system. The total energy of one of these parcels of mass in this Keplerian orbit is just going to be 1/2 m parcel. I'll just get rid of the subscript. V squared rotation minus g mass of the compact object, little m, divided by r. This total mass has to equal 1/2 of the potential energy from the virial theorem. Yes?
The virial theorem only holds if the angular momentum isn't changing?
It does, but you're absolutely right. But instantaneously, these things are just in their Keplerian orbits, right? So it's not actually all that bad to assume that. But you're absolutely right. Over time, you wind up having to slightly relax that because you're moving things in. What we're going to look at, and this is sort of where the big sort of derivation is coming now, is how we look at this total energy and how we look at that energy as changing as a function of radius and then also changing as a function of time at a fixed radius. And those two considerations wind up giving us the luminosity of the accretion disk, the temperature of the accretion disk, et cetera. But instantaneously, this is going to wind up generally holding. So this is just equal to minus g m over 2r. Try to be better about my little m's and my big m's. So let's watch what happens now. We'll be in our accretion disk here. We're now looking face on to this black hole with mass m. I guess I'll call it m1 just to make it easier in your notes. We're going to look at some sort of ring of mass at some radius r. And the total thickness is going to be something like delta r. As the radius decreases, assuming we wind up sort of satisfying the virial theorem, what winds up happening, we wind up getting more negative. E total becomes more negative. And in a black box sense, if we want that to happen, it means that we have to produce energy somewhere else, right? The energy, if the total energy of that parcel is getting more negative, where is that other energy going? And the answer to that, where is this E going? The answer to that is heat, which is the frictional force and the manifestation of the frictional force or the viscous process that's actually pushing this stuff inward, right? So it's all connected. Everyone agree with that? If I wind up changing E total, we'll wind up moving this parcel slowly inward as a function of time through these viscous drag forces, frictional forces. Then I wind up having an E total which is getting more negative. If I want to keep the total energy constant, then I have to wind up releasing some energy somewhere, right? And that comes in the form of heat. Is there a question?
Yeah. Is there an orbit where the parcel of mass is not falling into the black hole, where it's actually just stationary or even going outward? Like say in the solar system, we're not falling into the sun. We're actually moving a little bit away from it. right?
Well, that's from tidal forces and things. Yeah. So the short answer is no. The way that we've sort of set up our binary is such that everything that has a radius or along this distance between the center of mass of the secondary and the center of mass of the primary, everything to the right of this L1 line is going to be gravitationally bound with a negative energy associated with that. So it's going to wind up having some orbit here. Okay. When you have a lot of mass around, you wind up having this frictional drag or these viscous processes which drag the stuff generally inward. The reason why we don't have this in the solar system right now is because we don't have a tremendous amount of gas. The Earth has sort of swept out all the mass and all the particles and all the dust and everything in its own orbit. Early on in the history of the solar system, you actually get a tremendous amount of what's called planet migration. Because you take these large, massive bodies, and they actually wind up sort of smashing into various particles. So not only is their mass increasing, basically they're feeling these viscous processes which are pulling them inward. It is possible, because we have to conserve angular momentum, right? It is possible to set up a system in general where you wind up having something moving around, and you wind up transporting angular momentum out from the inner parts of the accretion disk. It winds up moving outward. In some cases, you might actually be able to blow off some mass moving in the opposite direction. But even a little bit of mass flowing outward can essentially sop up all the angular momentum of all the stuff moving inward. But for now, we were just happy with this thing becoming faster and faster and faster as it winds up moving in. As you probably know by now, the velocities of particles moving around a black hole are approaching the speed of light, right? So they're sort of keeping the angular momentum that they had when they were at very large distances and not moving very fast. Okay? Right. So where is this energy going? It's going to be released in the form of heat. This is what's going to give us the luminosity of an accretion disk. We can ask this question now, what the change of energy is as a function of radius as this parcel of mass is moving in. And this is just d by dr of minus g m1 m divided by 2r. So this is g m1 m divided by 2r squared. If I want to put the dr on the other side, I just get gm1 m dr divided by 2r squared. And now the interesting question is, how is this actually changing with time? So now I see that if I wind up moving this parcel of mass from the outskirts of this radius to this radius by delta r, this is the change of the energy of the system, or a change of the energy of the particle just from its associated motion and potential energy. And then we wind up having to liberate this equivalent amount of energy in the form of heat for us to make that move. So what is dE dt? The change with time. Well, this is just g m1 m 2r squared dr. And if I want to actually take this mass not changing, I can actually rewrite this as a dm dt. What's not changing it if I put myself at a fixed radius? R is not changing. Big M isn't changing. So the only thing that could be changing is the mass flowing through that radius, right? So this is just g m1 m dot divided by 2r squared dr, where m dot is units of, say, kilograms per second. It's the accretion rate, right? It's how much stuff is flowing in. In a steady state, that is where I basically have just an accretion disk and nothing's changing with the accretion disk. It's not piling up mass on the inner part of it, or it's not piling up mass on the outer part. All the mass that comes in from the secondary has to flow through and has to keep on flowing through, right? So the mass that's flowing through any one of these parcels in the accretion disk, if I'm in a steady state, has to be the same mass that's flowing through at the larger radius, right, of the accretion disk. So the accretion rate, or the mass loss rate, of the secondary turns into the accretion rate of the accretion disk. And in a steady state, that has to be the same number through every radius, right? So if I have a number like 10 to the minus 7 solar masses per year, which was sort of a typical number that I told you about, which I said was about a moon per year, that stuff has to sort of accumulate on the outer parts of the accretion disk, and then a year later, all that stuff has to be farther in, a year later, farther in, a year later, farther in. Depends on the time scale for this to flow through. But the point is that you have a tremendous amount of mass, which is now flowing towards this central body. Okay? In steady state, mass flowing from secondary is the same as what flows through the accretion disk. That heat that has to come out to allow us to get to a smaller radius, if you want to think about it this way, is radiated in some regimes of some configurations of disks as a black body. So here's my compact object. Here's my accretion disk. And what we say is that mass is flowing in like this over time, and we wind up radiating our heat outward with some temperature black body. Whoops. That's going to be a function of radius. And the reason why it's radiating as a black body is because, for those that remember from 7a, the optical depth of this accretion disk is much larger than 1. Right, so all the heat that's generated inside here, the inner parts, takes a while to sort of escape through the accretion disk. But there's going to be an effective photosphere, just like the photosphere of the sun. It's not an actual physical radius, but there'll be actually some sort of physical location where the optical depth is going to wind up equaling 1. Inside of that, whatever heat you wind up generating gets reprocessed, and you wind up having to emit as a black body. This isn't exactly true, right? Because I could actually have, iron, which is flowing inwards from this secondary, and that iron could become ionized or partially ionized, and it could wind up interacting with other particles around it. It could wind up becoming more ionized. So you can actually emit something in lines, right? You could actually wind up having absorption. But for the most part, we think of the emission from any one radius as being something like a black body. That's pretty good to 0th order. Okay, let's figure out what the luminosity of this black body is going to want to be. By the way, what is dE dt? Just the luminosity, right? So the way to think about it is, in steady state, you have this mass flowing in. For the mass to keep on moving inward, it has to release heat. When you talk about releasing heat as a function of time, releasing energy, you're talking about a luminosity. So we've already derived what the luminosity of an accretion disk is, right? Now we can relate that to the luminosity from a black body radiator. The luminosity from a black body radiator is just going to be sigma t to the 4th times the area of what's doing the radiating. Sigma t to the 4th, I'll say, as a function of radius. What's the area here if I look down again on this parcel? Right, so here's my parcel of mass at radius r in some size delta r along a given annulus, because I'm going to posit that the temperature is going to be the same at some fixed distance, right? Along a given annulus, what is the area that's doing the radiation? 2 pi r dr. Yep. What? Times 2. Yep, exactly. So we actually have two radiating surfaces. We have this area here, which is radiating downward, and we have another area radiating upward. So here's our top view, and it's the equals thing on the bottom view, right? Top. Bottom. If we say that dE dt, as we had before, is just the luminosity of the black body as a function of radius. Just rewriting this is just g m1 m dot divided by 2r squared dr is equal to 4 pi r sigma t to the fourth dr. Solving for t as a function of r, we wind up getting g m dot divided by 8 pi r cubed sigma to the 1/4 power. This means that TR is just going to wind up going like r to the minus 3/4, m dot to the 1/4 power, and m1 to the 1/4 power. As radius is smaller, as you might have already intuited, the temperature is going to be higher. And interestingly, the temperature of the accretion disk isn't super sensitive to the mass of the central body. So if I had a 1 solar mass object and I had a 10 solar mass object, 10 to the 1/4 is something only of order unity, right? So it's not such a significant difference in the temperature of the accretion disk. Neither does the temperature of the accretion disk matter tremendously on the accretion rate, this m dot. Put another way, if I want to change the temperature at a fixed radius from some central body, if I go from, say, a 10 solar mass black hole to a 10 to the 5 solar mass black hole, I only change the effective temperature by a factor of 10. Right? So what's vastly important in sort of understanding this temperature profile, not so much m dot, not so much m, but the fact that we have different radii of where we wind up doing the emission. All right, so it's hottest the closer we go to the central source. Any questions about that? Right, so now we have this luminosity because we actually have now we have the temperature. We can actually integrate that as a function of radius, and we can figure out the total luminosity of the accretion disk. You might have already guessed what that answer is because it has to wind up being this, right? But I'm going to wind up integrating it dr, so it has to be something related to that. The luminosity of the accretion disk is just going to be the integral of L as a function of r dr. And remember, we said that the accretion disk is going to have an inner radius and likely an outer radius, right? The outer radius can be no larger than L1 in the example that I just gave you. R inner, R outer. R inner for a neutron star is just going to be the surface of the neutron star, right? The radius of the neutron star. R inner for a white dwarf is just going to be the radius of the white dwarf. R inner for a black hole. Short-shield radius, except for the fact that everything within 3 short-shield radii is actually on these inexorably bound orbits that wind up falling inward. So what's called the last stable orbit around a short-shield black hole is something like 3 RS. So it's for a 1 solar mass black hole, we're talking about 10 kilometers, which is effectively the same radius as the neutron star, right? Anyway, so those are typical numbers. I'll give this to you in the form of a little table in just a minute. So this is going to be G m dot dr divided by r squared. There's a 2 down here. If r outer is much larger than r inner, then we're going to wind up having, when we do this integral of 1 over r outer is very big, so we're going to wind up, there should be a minus sign here. Is there a minus? Oh, no, that's fine. Yeah, put a minus sign there. Then we wind up basically having this term here go to 0, and this term here be something like an r inner on the denominator, and we wind up getting g m1 m dot divided by 2 r in. The total potential of all the stuff coming in is just gm1 m total of the accretion disk of the stuff that's being accreted divided by r inner, and the total potential divided by time is just going to be this divided by time, so this is going to be an m dot. So the total available energy in the accretion disk to be radiated away as heat is sort of 1/2 the total potential. If you had to work out what the luminosity of an accretion disk was to 0th order, hold on one sec, you would just say it's gm1 m dot divided by r with some sort of constants, right, that you have to pay attention to if you're going to do a full derivation. But this has got to be the right order because these are the only masses involved, and this is the only radius that's important. Is there a question? Oh, because this is already on the bottom. You're absolutely right. Thank you. My notes were right. Okay, thanks. Everyone get that? Thank you. Okay, so let's look at some examples here in the context of sort of stellar mass objects. Remember, I said last time typical mass or typical high end of an accretion rate might be 10 to the minus 7 solar masses per year. A more typical number you wind up getting is something like 10 to the minus 9 solar masses per year, and this turns out to be an accretion rate of 10 to the 14 kilograms per second. I'll make this little table for you, an object mass column, inner radius, luminosity, temperature in the inner part of the accretion disk, because now we can just plug in my numbers for my mass and our inner, and I can wind up getting a temperature and what sort of band this is radiating in. So we'll do a white dwarf, we'll do a neutron star, and we'll do a black hole. Typical mass of a white dwarf, say 1 solar mass, 1.4 solar masses of a neutron star. Black hole, we'll just say, for round numbers, 10 solar masses. Our inner, 10 to the 7 meters. The white dwarf is basically the size of the Earth to first order. It's like 6,000 kilometers. Depends exactly on its mass. So that's about right. Neutron star radius, 10 kilometers-ish. And black hole, what's the Schwarzschild radius of a 10 solar mass black hole? 30 kilometers. 3 times whatever the mass is, right? So remember, it scales as mass. The Schwarzschild radius, if you remember nothing from this class, is 3 kilometers for a solar mass. Okay, good cocktail party number to know. So this is 30 kilometers. So R inner, I said, is effectively sort of 3 times Rs. Luminosity, if you put in the numbers that we just wound up deriving for all these right here, is something like 10 to the 27 watts around a white dwarf. What's the luminosity of the sun? Does anyone remember?
23. No, 26.
26. Yeah, it's 4 times 10 to the 26 watts. So this is of order the luminosity of the sun. So an accreting white dwarf, we just figured out, has a luminosity comparable to that of the sun. Okay? Neutron star, that number is 10 to the 30 watts. And it's got to be comparable for a black hole. Temperature, the inner part of the accretion disk, using this equation right here, is, for a white dwarf, 5 times 10 to the 4 Kelvin. For a neutron star, it's something like 10 to the 7 Kelvin. And again, for a black hole, it has to be something comparable. If I just say like kT is equal to h nu, and then I figure out the wavelength associated with this temperature, then I wind up getting or I can actually just use Wien's law. I wind up getting something like a peak of the wavelength of 580 angstroms. Here I get 1 kiloelectron volt. Here I get 1 kiloelectron volt. Sorry if all this is sort of crunched in towards the edge of that board. This is ultraviolet. This is X-ray. This is X-ray. What do we conclude from this? Well, accreting neutron stars and black holes are very bright, thousands of times the brightness of the sun in luminosity. And they put out a lot of their energy, or at least the inner part of their accretion disk, is getting us into the X-ray regime. So these things are things that we should be looking for and finding in the X-rays. These white dwarfs are going to be radiating most of their energy at ultraviolet wavelengths and some at optical wavelengths, etc. The other thing which is immediately apparent, or should be immediately apparent, is the following. The characteristic signatures in terms of luminosity and temperature of a white dwarf, of a neutron star and a black hole, are essentially the same. So it's actually very difficult to distinguish accreting neutron stars and black holes from each other. So the way to actually do this is you might identify these objects at X-ray wavebands. And then use the Doppler technique from the secondary star to figure out what the mass of the black hole is, or the neutron star, and convince yourself that you're not actually looking at this. This picture here, it's actually kind of hard to see, is just to depict for you in your head the fact that when you have a neutron star or a white dwarf, you have this accretion disk which you're looking down onto this. The material can actually slam into the radius, right? And it can actually, the outer radius of the compact object, and actually either accumulate or just sort of detonate immediately. And so you might expect that you wind up getting these bursts, right, periodically from this system as you wind up building up this mass. But a black hole has no surface, right? So all the mass is just going to wind up flowing in. So all the energy that we wind up receiving from a black hole system comes from its accretion disk and cannot come from the surface because there is no surface. It's kind of interesting, I think, and useful to think about this accretion as an efficiency. Yes?
Can we detect a black hole when it's not in a binary?
What do you think?
Distinguish it from neutron star? I don't think so.
Well, something that you've done in your previous problem set, you kind of worked out what it'd be like to have a black hole accreting in the interstellar medium, right? So you have to have accretion, right? We already saw also from your problem set that Hawking radiation, the luminosity of Hawking radiation is just vastly small. So you're never going to see an isolated black hole in a vacuum radiating some nice sort of Hawking radiation that you could actually measure. If you have a tiny black hole, potentially, right? But for solar mass black holes, forget it. So that means it has to have some accretion. So if you have an isolated black hole by itself, and it's accreting the interstellar medium, you can work out the numbers and find out that that luminosity is actually quite low. What you really need is a very high accretion rate, because the very high accretion rate gives you high luminosity, right? Because luminosity is just going to go like m dot, and you need a very high temperature so that you can actually measure this in bands that distinguish this object from other objects. Okay? So let's think about this luminosity in the context of an efficiency of converting the rest mass energy into heat that we wind up radiating. So a totally efficient process would be to take some parcel of mass m and just turn all of that mass into pure energy, right? So here you might say the efficiency is equal to 1. I'll symbolize it with an eta. For fusion, we said that eta fusion mc squared could be liberated as energy. And eta fusion is 0.007. If we wind up writing this eta for accretion, one way to think about it is eta accretion is just going to be the luminosity that we wind up getting divided by the maximum luminosity you can imagine from turning all the accreted material, all of its mass, into pure energy. So this is just going to be gm m dot, I had a 1 over here, divided by 2 r in. What's the maximum luminosity that I can get if I turn all the mass that's accreting in to pure energy? C squared over the accretion rate? It has to be units of energy divided by time, right? M dot C squared, yep. Good. So we wind up killing the m dots, right? And we're just left with g m1 divided by 2 c squared r in. So now I can plug in my numbers here that I have over there, and I can wind up figuring out what these efficiencies are. Will you allow me to extend this like this? This is like the analog version of Excel spreadsheets when you have to add another column. Right, so this is for white dwarf. Eta white dwarf is 7 times 10 to the minus 5. I'm just saving us going through the numbers, but that's the equation that you wind up using. This is much, much less than fusion. Right, so if I took all this mass flowing onto a white dwarf from a secondary star, I don't get out a whole lot of energy for what I put in. For a neutron star, it's something like 0.07. That's much larger than fusion. So between fusion, which you think of this like great thing is, oh, that would save the planet if somebody figured out cold fusion, and accreting matter onto a neutron star, this is a vastly more efficient process, which itself is vastly more efficient than chemical processes. Black hole, it turns out you have to use GR to get these numbers exactly right. And for a short shield black hole, one that's not spinning, so A equals 0, you get 0.06. And for a maximally spinning black hole, you get 0.42. So this is the maximum amount of energy. If I have mc squared and I want to turn it into energy, the best I can possibly do in nature, effectively, is throw that thing into a black hole that's maximally spinning and I get 42% of its rest mass energy out in the form of heat. Eventually, right? Not instantly. On its way down, it's liberating its energy. Yes?
Where does the discrepancy come in with spinning and non-spinning black holes? Why is there so much more efficiency?
Well, why do you think?
Our energy is a lot less.
Right, remember we talked about the horizon distance of a spinning black hole, or actually an arbitrary black hole with A of 0 to A of 1. And we said that our horizon was gm over c squared 1 plus square root 1 minus a squared for a black hole. So if A is large, we actually wind up approaching a tiny horizon. It actually can't get exactly to 1, right? But it's approaching 1. We get to a tiny horizon, so our inner gets really small. But as I said, you have to do the sort of full GR calculation to figure out what's happening with the last orbits and stuff to get these exact numbers right. It's beyond the scope of this class. But hopefully that gives you a sense of why that's vastly different. Okay, any other questions? Yes?
Where does the other energy go?
Where do you think? Yep, could. It doesn't have to, though, right? So something that we'll maybe touch on at the very end of the class is the idea that this mass is flowing into the black hole, but just because it's heading towards the black hole and it's in this accretion disk doesn't mean that it has to make its way all the way into the black hole and actually serve to increase the mass of the black hole. Some of it you can imagine if you have lots of magnetic fields around, right? You've got a lot of ionized gas, and you have a tremendous amount of angular momentum in the system that you'd really love to get rid of, especially if you're near a maximally spinning black hole. That black hole is not going to allow you to throw any more angular momentum into it, right? So around maximally spinning black holes, you can't have something plunge in and conserve angular momentum because it can't spin any faster. So a large amount of mass has to flow outward, and that large amount of mass flowing outward has to actually carry a large amount of angular momentum. So what you wind up seeing around most black holes are these things called jets, which are just basically emanating from the central object, but instead of all the mass, what's called advecting in, or just flowing inward to the black hole and disappearing forever, a large amount of it's flowing outward, and you have a tremendous amount of sort of rotation within these jets. Not only that, you also have large amounts of magnetic fields, you have charged particles, et cetera, and those charged particles, in the presence of magnetic fields, winds up radiating, and we can see that radiation in those jets. I think it's reasonable to start asking what kind of evidence do we actually have for disks. Can I erase this? Well, can I erase everything that I haven't erased already? Yes, okay. The most obvious thing you can imagine in terms of looking for disk is just imaging those disks. These disks, though, are quite small. And so we don't actually have direct images of accretion disks around black holes or neutron stars. Instead, if we look at the circulation of the matter flowing around, and we wind up looking, say, edge on to this disk, here's you looking, we have some material which is going to be blue shifted, and we have some material over here which is going to be red shifted. So what does that actually translate into? Something that we could observe. Here's flux as a function of frequency. Here's some sort of what's called double-peaked emission. This is the rest wavelength. Here is the blue shifted component. Here's the red shifted component. And if we make some measurement of delta nu, as we said at the beginning of class, delta nu divided by nu naught is just going to be equal to the rotation speed of this disk divided by c. And this is actually seen in accretion disks, or inferred in accretion disks around white dwarfs. So you can actually see this component. But something that's kind of cool that actually ties in together special relativity and general relativity is for us to now start thinking about what happens in the really inner regions around a black hole or a neutron star where general relativity actually becomes important. First of all, just from special relativistic considerations, say that this material is moving now something close to the speed of light. Is the blue shifted component or the red shifted component going to be brighter? And they will have a different brightness. All other things being equal. Why? Well, but you have an equal amount of material redshifted as blue shifted. Not gravitation. I don't want to get into gravitational redshift yet. Why? No, I don't want to do I don't want to do gravitational redshift. And this isn't moving on the sky, so I'm not dealing with transverse relativistic Doppler effect. There's a different kind of Doppler effect. Doppler beaming. Yeah, stuff moving towards you is beamed towards you. Stuff moving away from you is beamed away from you. So indeed, the blue shifted component, when you're moving at very high speeds, can actually be brighter than the red shifted component. That's one effect. Okay, so we did special relativity. What's the gravitational redshift effect? The whole thing is going to wind up being redshifted. And in fact, what you can do is look at nu obs versus nu emitted. So here you'd have to be very careful about what nu zero is. And you can wind up showing that in some cases you wind up getting nu obs is something like 2/3 nu emitted. So in this case, nu zero has been overall gravitationally redshifted by something like 2/3 the emitted rest frequency. And that's just 1 minus rs divided by r to the 1/2 power. So that says that you could get a radius where you're doing this emission of something like a few rs. So this is the gravitational redshift. And to make these measurements of these different lines, of course, it can't just be a pure black body. In particular, what we look at are iron emission lines from the system. What's really neat about being able to look at iron emission lines, turn the lights down a little bit, is that you actually have access to perhaps the spin of the black hole. This is a depiction of a non-spinning black hole on the left-hand side and a spinning black hole on the right-hand side. You have an equal amount of mass flowing in. The mass is the same. So our equation effectively for the luminosity should wind up being the same overall. But here's this, there's some rest wavelength of this line. You can see that it's almost sort of double peaked right here. But you get a tremendous amount of blue shift increase because the material moving towards you in the inner accretion disk is Doppler beamed. And the stuff moving away from you is actually Doppler de-beamed, or it's pointing away so you get less flux. But what you wind up noticing is that if you have this stuff coming out from a black hole that's spinning, you wind up noticing that the whole thing is shifted over by a little bit, but you get a huge amount of redshift tail because you've gone so far into the potential that the stuff that's being beamed away from you is also experiencing a large amount of gravitational redshift. Just sort of see if we can depict that. There'll be a little sort of depiction of our iron line here. Watch, it's basically following and tracking the hot spot. Coming towards you, it gets brighter, away from you, fainter. Towards you brighter, away from you fainter. Now we'll get another hot spot in there at a larger distance. You see that the change of the overall height for this red thing is not nearly as much as the yellow thing. And so you just build up the whole flux from the accretion disk, and these are models that you can wind up making, and that winds up giving you this overall structure of this so-called iron line. Measurements. These are actual measurements. One of the first sort of bona fide great measurements of relativistic motion around a black hole. And in this case, the line is so extended that you can actually get some evidence that this black hole is spinning. So this is one of the main ways that you can get measurements of black hole spin. In this case, because the radius of emission turns out to be smaller than 2rs, the effective short shield radius if it wasn't spinning. And so you actually get emission from what would have been within the event horizon if it hadn't been spinning. So this is just a model to the data, and you can imagine, there's some errors in the data itself, and the models are going to have some uncertainties associated with them. But this is the kind of thing that people try to do. They make an industry out of measuring black hole spins. See, now you know why we had to go through all this GR and SR stuff, so we could get to all this gee whiz. Any questions about that? Well, no. So that's an interesting question. In principle, all that's taken into account in those models. So it's not. So it's not something that you could immediately disentangle from the spin. The fact that it's spinning is causing the frame dragging, which is causing the event horizon to be smaller. I don't know if there's any independent evidence for frame dragging from black holes. They're all sort of entwined. Okay, so in the last 15 minutes, I want to talk about supermassive black holes. We've basically just been focusing now on stellar mass black holes. And these are these things that you've read about already called quasars, or active galactic nuclei. I just want to do some of the numbers of what kind of masses we're looking at in the typical luminosities. So AGN, active galactic nuclei, sometimes called quasars. And as you saw, there's sort of a whole zoo of different types of active galactic nuclei, Seyfert galaxies and radio galaxies, etc. The thing to recognize is that we didn't know about these things until the 1960s, and the first observations that were made were basically of just some radio star. There was a star that had some radio emission. People didn't know what it was because it's kind of weird to have radio emission. I mean, until like the 50s, really the only type of astronomy there was optical astronomy. And then there was radio astronomy. And then there was X-ray astronomy. So there are all these bands that were completely inaccessible. So as soon as they started turning on radio receivers and looking at the sky, one of the first things they found were pulsars. But the next thing they found were basically radio stars. When the radio star was looked at optical wavelengths, it looked like a really weird blue star. It was compact. There was no evidence for any extension at all. And somebody named Martin Schmidt at Caltech, SCHMIDT, took a spectrum of this famous radio source called 3C273, and he called it a quasar for quasi-stellar object because it was sort of like a star, but it looked something very different than that. And he wound up inferring a redshift. This is now a cosmological redshift. We'll talk a lot about that later on, of this thing of z equals 0.16, implying that this star was moving away from us at something like 16% the speed of light. And they knew by that time, obviously thanks to Edwin Hubble in the late 1920s, that redshift in a cosmological sense usually translated into distance. And we'll see all this stuff later on, but that corresponded to a distance of 680 megaparsecs. To remind you, parsec is 3.085 times 10 to the 16 meters. So this is a distance of something of order 2 times 10 to the 25 meters away, if you just use the cosmological redshift. Just introducing the fact that there's this third kind of redshift that you haven't seen yet. We'll do a lot more on that later. The total flux across all the different wavelengths was something like 2 times 10 to the minus 13 watts per meter squared. And we know that flux is equal to luminosity 4 pi d squared. This implies a luminosity of 10 to the 39 watts. The luminosity of the sun, as we said before, is something like 4 times 10 to the 26 watts. So this is of order twiddle 10 to the 12, 10 to the 13 solar luminosities. So this little blue star, albeit at a very large distance, not a star at all, but point-like, was producing 10 to the 12 solar luminosities. That's pretty remarkable. I'll show you a couple of pictures of this. There's our little blue weird object there on the left-hand side. An optical image of 3C273. Looks really no difference than anything else there. Here's a picture of Martin Schmidt. And here's a spectrum. You don't have to know the details of all this, just sort of showing you these classic results. So red wavelengths on the left-hand side, blue wavelengths on the right-hand side, so wavelength increasing to the left over here. This is a comparison spectrum of hydrogen lines. And what he wound up noticing is that you had to move this whole spectrum. This is H gamma, H beta. You had to move this entire spectrum by a whole amount to match up all these different lines. Pretty remarkable. This is the actual data, right? Pretty remarkable that somebody could make an inference in the 1960s. But this is obviously now routinely done where we get spectra of different objects. In fact, you can even do this in a spatially resolved sense where you put a little spectrograph across a nucleus, an active galactic nucleus, and you wind up seeing basically very large Keplerian orbits of stars swirling around these different objects. This is a Doppler redshift. What Schmidt wound up measuring is a cosmological redshift, and the two of these effects are both actually at play. Let's figure out what 10 to the 39 watts is in Eddington units. Everyone remember the origin of the so-called Eddington luminosity?
It's the maximum luminosity before it starts blowing out.
Yeah, so you have this luminosity, right? What's special about photons as they're streaming out from some central source? There's radiation pressure, right? So if you're going to feed this system, say through accretion, and you have mass all flowing in on, sort of all flowing in, not necessarily on an accretion disk, but just coming in at all from all distances. If I want to now actually not blow out that source from the luminosity that I've produced, all of that mass has to flow in, and I have to wind up producing a luminosity which is less than the Eddington luminosity, the so-called Eddington luminosity. Just to refresh your memory, this is from Carroll and Osley equation 10.114. The Eddington luminosity is 1.5 times 10 to the 31 mass divided by solar mass watts. If I just associate this luminosity of this source with the Eddington luminosity, what do I wind up getting? Something of order 10 to the 8 solar masses. For the object that's producing, if I say that it's all coming from one place, for the object that's producing the energy from 3C273. Okay, so that's one consideration of how we might actually infer this, the mass of this object. But probably more interesting, in fact, more interesting, is the fact that we have X-ray flux from this quasi-stellar object. This X-ray flux, as you probably just saw when we were deriving our temperature, we now think comes from the inner parts of the accretion disk. The X-ray flux changes brightness on hour-long timescales. Why is that interesting? Well, if you have something which is a blob which is lighting up, and it takes sort of an hour for it to change its brightness, it makes sense that that blob is something of size 1 light hour at sort of smallest, right? It could be bigger than that. So you're thinking about something which is 1 light hour across. So you think about something which has an emitting radius, which is just c delta t. And this is, just putting in the numbers, 7.2 times 10 to the 11 meters, which is a few astronomical units. In AU, 1.49 times 10 to the 11 meters. So this is a fairly small emitting region that's producing a tremendous amount of luminosity. And from that, we might actually now start figuring out what the total size is if we wind up associating this size with the inner radius from a black hole. So if we say the inner radius of the black hole is something like 3 times the Schwarzschild radius, and we associate that with this R, call it R X-ray, we get a handle on what this radius is going to wind up being. So this is going to be 6 gm over c squared is equal to a few AU. And you can work out the numbers here. This means that the black hole mass is something like 7 times 10 to the 7 solar masses. This is all sort of hand-wavy numbers of 1 hour long. But you get the same answer for the Eddington luminosity. This is more interesting, right, because this is more of a direct measure of the sort of size scale of the region that's doing the emission. And the fact that it's so close to the Eddington luminosity is really interesting. Right? It says that this black hole is essentially radiating somewhere near the maximal amount of energy that it could be radiating. What's m dot here? What is m dot? Remember we said the luminosity of the disk is just g m dot divided by 2 r in. So m dot, if we just wind up solving for this, is if we put in the numbers, something like 1.3 times 10 to the 23 kilograms per second, which is a tidy 2 solar masses per year. So to get that luminosity that we wind up measuring from a black hole that has this mass, whose mass we wind up inferring from these sort of timing arguments, we need a total mass inflow of something like 2 solar masses a year from this stuff. Indeed, and I'll end with this, if you make a plot of nearby supermassive black holes whose masses have been measured as a function of their optical luminosity, essentially just their brightness in these different units, and you actually make a plot of the Eddington luminosities inferred from those masses relative to those luminosities, Eddington luminosity is up here, 10% the Eddington luminosity is here, 0.01 times the Eddington luminosity is here. And it turns out that all of these black holes in the local universe like to radiate at something like 10 to 20% of their Eddington luminosity. Which is kind of neat, because if you make a measurement of an optical luminosity of a quasar, so boom, there it is, you know, or you can infer what its mass is if you just wind up invoking this argument. It's not clear physically why these black holes have to radiate at Eddington luminosities. In fact, you can imagine why they might be able to radiate at larger than their Eddington luminosity. Eddington luminosity is derived assuming sort of spherical inflow of all this mass, and you assume that this mass isn't getting blown out by the pressure from those photons. But remember, we said the mass is actually flowing along the accretion disk, and then I could radiate out from outside of that. So it's not clear why Eddington luminosity is sort of this sort of upper limit here. Turns out that there's some instabilities that wind up growing when you get to Eddington luminosities. You wind up impinging photons on the disk, and you wind up creating instabilities in the disk, and the disk sort of disrupts. So to have sort of this steady flow of mass around supermassive black holes, you need to radiate at something less than Eddington luminosity. But all the details of that are not really well understood. Okay, so I'll end with that. Good luck on your studies. And remember, sections as normal. I have special office hours next Monday from 4 to 5. There's an interesting colloquium today. In-class exam. Calculators, cheat sheet. Review section, 6 to 8 on Monday.